that we are going to have. So we are going to cover topics in calculus and topics in algebra, in linear algebra today, and for that I will also record some videos so that after lectures you can follow on those videos. So what I want to do today, what I want to do in this session, I want to talk about calculus, and what we are going to talk about, we're going to talk about derivatives. So we will talk about derivatives in two cases, the single variable case that you hopefully all know, and then the many variable case. Okay? And so we will talk about derivatives, and then after that, during when we talk, I'm going also to show you some applications of these two financial calculus to finance. Okay, so what is a derivative? Okay, so the classical definition that if you have a graph, okay, let's say this is your graph, y equals f of x. Okay, and what you want to do, you want to have a tangent at this point to the graph, and then you ask yourself, what is this angle, or what is the slope of the line? And the slope of the line will be exactly f prime of x, the derivative of x, of f. Now, this is a classical definition. This is what you are going to see in every calculus class. But the more important thing for me is that you guys can understand that this is actually a great calculating device. Okay, and it's heavily utilized by traders that are sitting on the desk. Why is that? Because you have the key formula that f of x equals to f of x0 plus f prime of x times delta x. Okay, now what is delta x? Delta x is x minus x0. So if you know the function at this point here, okay, and you want to find the function to a close point of x0. So, for example, you know the function, you know the point here, and you kind of know you want to find this value. So what you want to do, you get the best linear approximation. So you are going to have a tangent, and what you are going to say that my function is actually approximated by the corresponding point in the function. So if you increase it in a microscope, this is your graph. Let's say that this is your point, and then if you have a point here, you will take its value to be this value here. Okay? And this is a key formula. Now we have the usual rules. I do not want to prove these rules, but I will just remind you. So first of all, the derivative of the product is going to be the product of the derivatives. And then the derivative of the quotient is going to be basically, and then you divide by g squared. Okay, so these are the first two rules, and the third rule, of course, is that the derivative of the sum is going to be the derivative, the sum of the derivatives. So for example, okay, suppose you, and then you also know that the constant is going to be 0. The derivative of the constant is going to be 0 because it's going to be like this, so the line is tangent to itself. Okay? So for example, let's say that you want to calculate the derivative of x squared. Okay? You want to say what is x squared. So then you know that this is x times x prime. You can say that this is the derivative of the first, so it's x prime times x plus x times x prime. So this is your f, and this is your g. Okay? Why is it important? Well, think about this. What is the derivative of x prime? Well, if you look on this formula, you know exactly what the derivative of x prime, because then you know that exactly x plus delta x equals to something, x0 plus delta x equals to something, here's the derivative, time plus delta x. So if you solve this equation is going to give you that f prime of x, 0, is just 1. Okay? So you have something like that. So then you have that this is 2x. And in general, of course, x n to the prime equals to n x to the n minus 1. Okay? What other functions are important in finance? Okay? The other function which is important in finance is exponential function. Where does the exponential function comes in? Well, think about the fact that you want to actually calculate interest rates. So we will talk about this a little bit more in class when we will start the course, but interest rate can be calculated in discrete or continuous. And I'm focusing on the continuous. So what is this continuous calculation? Continuous calculation is when you reinvest constantly. You reinvest all the time, right? So then, if you invest $1, okay, and you reinvest constantly with a rate R, let's say, which is an annual rate, but you reinvest constantly, then the number, then your value, your money, after time t will be e to the rt. E to the rt. Okay? This is your exponential function. And e, okay, just to remind you, e is going to be 1 plus 1 over n to the power of n, and this is a limit. All right? What is going to be the derivative of this function? The derivative of this function, okay, we need to, in order to understand the derivative of this function, we need first to have two ingredients. The first one, what is the derivative of e to the x prime? The derivative of e to the x prime is e to the x. This is your first rule. But here we have r times t. So it's not, it's a little bit different, right? Because first of all, what is it? We want the derivative with respect to r or to t. We want the derivative with respect to r. Because what we want to understand is if I'm moving the interest rate, let's say, a little bit by up or down, what will happen with the value of this instrument? What will happen, how much money I'm going to get? Okay? So here, what we are going to have here, this is good, but you have r times t and you want to have a derivative of r. So what do you do here? Well, what you do here is you use something which is called the chain rule. And this is like the most important rule that you have in calculating derivative. What does this chain rule means? The chain rule is as follows. If you have a function g, and here you compose it with a function x, like this, okay, then the derivative of this guy evaluated at x is going to be basically the derivative of g evaluated at x, at f of x, times the inner derivative, which is f prime of x. Okay? And this is a very important rule. This is basically the key rule that makes this thing work. Okay, so how does it work? How do you use this rule? So let's say that we want to calculate something of the form e to the c times x. This is exactly what we have here. So how do we apply this rule? So g is going to be e to the x. What is f? F is going to be c times x, okay? So we compose two functions together. We have the exponential function, and we are calculating it not at e to the x, but c times x. So we are actually composing two functions together. This is what is called, this is a composite function, and this is called the chain rule of a composite function. Okay? How do you calculate this? So in order to calculate this, you need g and you need f. So g, we said e to the x. What is f? F is going to be c times x. So when you calculate this, what will you get? You will get e to the cx times c, because this is going to be the g prime of f of x. This is going to be e to evaluate at c times x, because the derivative of e to the x is e. Okay? And here you have c times x. So here you are evaluating at c times x, so the derivative of c times x is going to be c. Okay? Once again, you can think about that in the following way. Cx prime is just a product, so it's c prime times x plus x prime times c. Okay? And we know that c prime is 0, so this goes away. You have x prime times c, which is c. So here, okay, you are going to have e to the power of cx times c. Okay, conclusion. Okay, what it means here, that if I'm going to have a derivative here of ERT prime, okay, I'm going to have here r to the ERT. Now, why is it important? Why is it interesting? Suppose you want to understand, okay, how does your instrument moves if the interest rate goes up or down. So let's say now that you have the following example. Let's say that you have basically r equals to 0.01. So your r is 1%. Okay, and now what you want to do, you want to quickly estimate, okay, by how much this instrument moves. Okay, now, so then what you are going to have is the following. You will say, okay, say my value now is e to the r 0.00, let's say t equals 2. So my value now is going to be 0.01 times 2. And now let's assume that r now moves to 0.02. So this is your r0. r1 is going to be 0.02. And now what you want to do, you want to estimate at e to the 0.02 times 2. So now you have two ways to do it. Of course, the first way is using a calculator. You can just take your guy and you can just do it with a calculator, right? But the other way, and we're going to see why is it available, you can do the following. Because, you know, on the desk, when you have seconds to decide on a trade, you don't have the benefit of the calculator. So what people are doing, I'm going to show you now. They're going to use a derivative. So they are saying, okay, what is going to be delta r? So delta r is going to be 0.02 minus 0.01. Okay, this is your delta r. What is going to be my derivative? My derivative is going to be r. We said that my derivative is c to the x times c. But what is c here in our case? Because we're deriving with respect to r. So rt is 1 or 2 or whatever. Okay, c equals to t here. Okay, I know that it's very confusing, but if we have e to the rt, we can derive with respect to r. T is constant, so r is a function, okay? So it means that here, okay, t is our constant, is our c. Okay, so you are going to have delta r equals 0.01 minus 0.01, which is 0.01. Great. And now what you are going to have, you're going to evaluate the derivative. And we know that the derivative is basically t, which is, let's say, 2 times, okay, 2 times e to the 0.01 times 2, for example, times 2. Okay, this is going to be your derivative. So now you are saying, okay, I know this value because I calculated it before. So it's 2 times this value, and then I need to multiply by 0.01. So I have 2 times value that I know, and then I'm going to multiply by 0.01 because this is my delta. So I know that my price now is, the change is this. So my final price is going to be basically e to the e to the 0.01 times 2 plus 2 times this value, e to the 0.001 times 2 times 0.01. Okay? Do you see how it works? Because if I know this value, as a trader, if I remember this trader, I just need to mentally multiply it by 2 and then take a percentage and I'm done. I know exactly by how much this moves. Now, which is very important to remember, okay, that and I repeat, this is not precise. But this is a rule of thumb. So it's enough if you are on a desk and if you do something like that, that's enough. Now, what you care about as a financial professional, okay, is not just the absolute movement, you care also about the return. Okay? So how do you handle the return? What is the return? Remember that returns are as follows. So you basically have something like that. So if you have y1, price 1, and price 0, okay, your return is going to be p1 minus p0 divided by p0. This is going to be your return. Okay? Now, how do you handle this, you know, in a calculus way? Okay? This is just going to be delta of the price. And then you have the delta of the price divided by the price. Okay? What is delta of the price? Delta of the price is going basically to be, we know this formula, we can say the delta of the, let's say the delta of the price, we can say that, let's say that we are going to have a function of x. And x is some variable, doesn't matter what. For example, here, x can be r, okay? So you have p0 of x, p1 of x, okay? So you have something like this. You're going to say, okay, this is going to be basically p1 of x minus p0 of x divided by p0. And now I will do the following magic. I will say that this is going to be delta p divided by p. But what is delta p? I can say that this is p prime of x0 times delta x divided by p. Okay? So what I'm getting here, that I have a derivative. I have a quotient here. I have a quotient here, and I multiply it by delta x. So where is this quotient coming from? This is actually a very interesting story. So let's look on the log. So what is a log? I remind you that if you have a log of E, let's say of EA equals B, it means that E to the B equals A. So E, for example, log of E1 equals 0, then log of E square equals 2, log of E square root of E equals to half. Log is a very important function, and it has the following wonderful property. It has many wonderful properties, but the following property is very important. The log of A times B equals to log of A plus log of B. And if I want now, here I did not denote the basis. So if I really want to be Pope, if I want to be very, very precise, I need to say that this is ln of AB equals to ln of A plus ln of B. What is ln? Ln is going to be this logarithm with a natural number e as a base. Okay, this is true for any base. So for example, here you can say log of 10. What is log of 10? So log of 10 A equals B means that A equals 10 to the power of B. All right, so that's it. Okay, now what is going to be, okay, the derivative of log? Well, this is kind of interesting because we can use the chain rule to do that. Indeed, I can actually say that e to the power of log x of ln x equals to x. That's by definition. Now I'm going to apply the chain rule here and here. So if I'm going to apply the chain rule, what am I going to do? So here I'm going to have 1. What am I getting here? So it's going to be e to the ln x times the inner derivative, like this. Okay? Because this is exactly the definition of e to the power of ln x. Think about this as a composite function. Okay, then use g equals e to the x, f or e to the z, and then z equals to ln of x. And use the fact once again that g f of x prime equals to g prime of fx times of f prime of x. Okay? So what you have here is that this is x, so you have x1 over x equals 1. Okay, so you must have that ln of x prime equals to 1 of x. Now go back to here. Go back to the return, to the formulas that we have for the return of delta p divided by p, or alternatively px divided by px. Look, what is the derivative of logarithm of the price? That's exactly going to be p prime of x divided by p of x because of that. And once again, we're using the chain rule. Use the chain rule all the time. The chain rule is the bread and butter of calculus. Without chain rule, calculus is worthless. Okay? The most important rule in life. So p prime of x divided by p, look at that. We said here that delta p equals to p prime of x delta x divided by p. Okay, so here, what you are getting here is d of log p. So now we are having a wonderful conclusion. And what is this wonderful conclusion? That if you want to calculate the return, by how much, what is, or you want to estimate the return, what you can do, okay, instead, when you look on a function p, okay, in order to calculate the return as a function of x, let's say, okay, in order to calculate the return, you need to take the log of p prime, okay, and to multiply by the change in x, assuming that your price is a function of x. Let's look on this case of these guys, okay? So now we're going to talk about something which is called the zero coupon bonds. Okay, and what are those zero coupon bonds? Zero coupon bonds basically are instruments where you buy, where you buy today and it will give you $1 in the future. Okay? How do you evaluate such an instrument? Well, if today you buy something, okay, in time t, you are going to have e to the rt here, right? So if you, for example, invested $1, you're going to have e to the rt. So what you want to do, t is a time, t is a maturity. Okay, so what you want to do here is to say, okay, if I have e to the rt, when I have one, how much I'm going to have $1 here? Of course, if I have e to the minus rt here. So this is your zero coupon bond. What you want to understand is how is the return of zero coupon bonds insensitive to r? Okay, so if you move, let's say, r by 1%, what will happen with the return of the zero coupon bond? And here comes our formula. Okay, all we need to do, okay, is to look on the derivative. We said we need just to look on the derivative of log e to the minus rt, okay, and we derive it with respect to r. Because r is our function. Remember here that we had, okay, d, that p prime of x divided by p of x is just d log of px. Okay, so log of e to the minus rt. So what is log? What is log with respect to basis e of e to the minus rt? Is just going to be minus rt. Okay, the derivative of d to the d minus rt is minus t. So what does it mean? It means the following. Say if let's say that my yield or my interest moves by, let's say, 1%. Okay. Your bond value will return minus t times this 1%. Okay? This guy, okay, is not, this guy is very important in finance, and minus this guy is called the duration. So you can think about the definition of duration as follows. Duration of an instrument, of a fixed income or any instrument, okay, the duration of an instrument is just going to be minus the log of the price, okay, where you are actually taking the derivative with respect of some x, like this, okay? That's it. Now, it's a very powerful tool. Why? I'll give you, and we will do this exercise in class. In the class, say I'm giving you, let's say R equals to 0.05 and T equals to 2. And I'm asking you, okay, if you are a fixed income professional and you want to estimate what happens with your portfolio if R goes from 0.05 to 0.055. So what does it mean to estimate what happens to your portfolio? You care about the return, by how much the portfolio will change. Okay, it's easy peasy with this. Okay, we know that it's going to be, so we know then delta R is just, we said that this guy, dx log p times delta x. Okay, so here what you are going to say, okay, that's not a problem. I know that my derivative here is minus 2 because t equals 2. So the bond will mature in 2 years. So you are here and the bond will mature in 2 years. Easy peasy. So it's minus 2. And we say that R goes from 0.05 to 0.055. It's going to be to 0.005. It's going to move by 1%, minus 1%. Okay? So this is a very important thing in fixed income instruments. When the interest rate goes up, this is interest rate, bond price goes down. Okay? And the rule of thumb, and this is very approximate, this is not correct. Okay? And the rule of thumb is that this is going to be minus 2%, minus 1%, because you take the derivative minus 2 times 0.005, which is the difference between those two guys. Okay? So you have minus 1%. Okay, so I hope that this is clear. Now, okay, so here you could do it in a heartbeat. That's the great advantage of these technologies. That's the great advantage of of these derivatives. Another example is in the Black-Scholes formula. So what is the Black-Scholes formula? The Black-Scholes formula, if you there are instruments which are called options, and this is something like this. You have the option, okay? You have the option to buy a certain instrument with a prescribed price. Okay, so you'll talk about this, during the course, during the years. But here I just want to give you some taste of how powerful this thing is. Okay, so it means, for example, that if you're if the price in which you can buy it is going to be K, which is going to be a strike price. Now, suppose you are managing portfolios of options and you want to understand how does the value of option changes. Once again, now we're not talking about returns, we're talking about absolute change. There is very important to understand the difference between absolute change and and not absolute change. Okay? So let's say that your option value is V, and this is a function of S, where S is your price of the underlying instrument. Okay, so here you have an instrument that you can buy, and that instrument is called the underlying instrument. Okay, now the price that you can buy it for is called K. This is a strike price. And the rule of thumb is that if the instrument moves by $1, okay, that's the derivative. If S, okay, if the price of the stock equals K equals to the strike, okay, so here you have an instrument that you have an option. So if the price of the option of the instrument is $200, your strike is $200. So you have the option to buy this thing for $200 when you are in the future. Okay? And okay, so this is an instrument. Now you know that V prime of S when S equals K is equals to around half. Okay, and now you're saying to yourself, okay, what happens with the value of my instrument? Okay, if for example, if my stock is going to go from 200 to 201. You want to quickly estimate by how much the price changes. You don't care, for now, you don't care about the price itself of the option. You want to get the estimate, because the estimate is the most important thing, right? So if you go from 200 to 201, okay, you know that your delta x equals to 1, because it went, or delta s equals to 1 because it went from 200 to 201. So here you know that it's 0.5 times 1, so it's 50 cents. $0.5, yuans, rupees, whatever you want, and it's 50 cents, okay? That's all there is to it. The sensitivity analysis, which is initialized by these derivatives, is a key approach and the key metrics in portfolio management and in risk management as well. Because that's exactly what risk management is. You want to understand how your instruments behave in a quantitative way if your underlying instruments move. And that's exactly what you have here. Okay, another example is something called the CAPM. And it's a theory which says that if you have a stock price, let's say that you have a stock C, its price, its returns, not its price, but its returns is more or less beta times what we call the return of the market plus some alpha. Okay? What is this beta? Beta tells you exactly what happens with the return of your stock if your underlying market index moves by a certain let's say 1%. So beta tells you, so if beta equals to 3, it means that if this guy moves by 1%, then this guy will move by 3%. Now, why is it important? It is important for financial professionals because if you don't have alpha here, you can actually reconstruct C by just buying more of this guy. Okay? So for example, beta equals 3, there is no alpha, there is no basically intercept. Okay? What you are going to get, you are going to say, okay, I will buy here instead of buying the stock C, I will buy this market. So for example, instead of $1 here, I will buy $3 here, and it will be the same effect. So when you have something like that, you can reconstruct the stock through the market, okay? Because of this beta, because of this sensitivity, which tells you, okay, if this guy moves by 1%, I know that this guy will move by 1%. Okay, the change. That's what is important. So we will talk about this more during the course, but I'm just giving you some hints of how this will work. And let's think, last example for this video. And I'm going to do it much more in the class. Let me give you a certain algorithm, which is basically a basis for all the machine learning algorithms out there. So all the machine learning algorithms out there are basically children of what I'm going to show you right now. So what do I want to show you right now? So if I have f of x equals 0, I want to solve this equation. Okay? Now, f can be any function. That's the problem. The problem is that if f is like x plus 5 equals 0, you know that x equals minus 5. Okay? So how do you approach, in general approach, how you can solve this equation? Okay? So here's the secret to that. What you want to do, you want to say, okay, let's say that I'm starting with a point f of x 0, and what I want to do, I want to actually come close to 0. Okay? So then what you are going to say something like that. Let's say that f of x 0 plus delta x, for some delta x, this is going to be my, I'm going to change this point by delta x. How can I, what is this? This is going to be f of x f of x0 plus f of f prime of x 0 times delta x. Okay, and now you're saying, now you're doing the following thing. You're saying, okay, this equals to 0. It means that this equals to 0, okay? This is approximate, of course. This equals to 0. How can I handle this? Let's assume that this equals to 0. Let me solve the equation. So it's going to be the, and I'm looking for delta x, because what I want to do, I want to, if I have a graph and I'm here, I want to come closer. Let's say that it intersects here. I want to come closer to 0. So this is what we call a descent. So you are here and you want to start to go towards, towards the x-axis. So you're saying, okay, if I'm something like this, I'm going to say that my delta x is going to be, okay, so let's do it, right? I mean, it's going to be f of x0 plus f of x prime x0 times delta x. If this is equals to 0, so delta x is going to be minus f prime of x0 divided by f of x0. So what you want to do, you want to actually take this x0 and you move it by delta x. So geometrically, what does it mean? That if you have a graph and this is your tangent, you're going to find this point where you have the tangent intersection, and then you are going to move this guy by this point. That's the idea. Okay, so now you have something like that. Bang, 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 until you reach x. Okay? The differences are getting smaller and smaller and smaller. This is, this function, which is very innocent, okay, is basically the basis for all the algorithms of machine learning out there. When you talk about backpropagation and descent, this is what is going to happen. And we're going to talk about it in couple of next videos when we're going to talk about multi-derivative calculus. Okay, so great talking to you, and I hope that you enjoyed the first video on that.